Welcome back. This is Tutor Wizard. I'm Adrian. Please subscribe right here. Hit the notification bell below. You'll get notifications for this series and a bunch of others on our channel. We're doing Linear Algebra 1. This is Chapter 1, Systems of Linear Equations. 1.6 is going to be the augmented matrices and row operations. This is going to give us a systematic method of solving n by n linear systems. Therefore, this lecture, we define the augmented matrix of an n by n linear system and the three row operations that we're going to use to systematically solve n by n linear systems. Let's do that. Nice figure. I know, that's so nice. Somebody's jealous because we got new kitties. Okay. That's Jasper. She's hanging around. You just don't want to be picked up. You just want to be nice. Okay. So what we're doing is, let's recap one more time. She's going to hang out down here because the little cats are running amok upstairs. We have a linear system. It consists of m equations, or rows we're going to call them right away. And then we have n columns, or variables, x1 to xn. And so in your mind, as we start doing this, we're going to interchangeably a lot of the time think about having an m by n system. M is going to mean the number of equations or the number of rows, I'm going to consistently say. And n is the number of unknown variables or columns in the coefficient matrix that we're going to start discussing in a second. A solution to a linear system is any ordered n tuple S1 to Sn, which makes all of the equations true simultaneously. We went over this in the previous video. And by solving a system in any scenario, by solving something, we mean find all of the solutions to this, and we write it in what we call the general solution. And of course, there can only be 3 scenarios for this. In that scenario, we can have a nice flow chart eventually. A linear system S with at least one solution is called consistent. And the parasitic definition, therefore, is a system which doesn't have a solution or no solutions is called inconsistent. And then we already have, I keep repeating this, and then in about 1 or 2 more videos, I'll finally state this as a theorem, which we probably won't prove in the video, but we have proved this. And it's going to say that given a linear m by n system, there's only 3 cases. If it's consistent, there's either one solution or infinitely many solutions, or if it's inconsistent, there's no solutions. What that means is we get a nice flow chart eventually, which we're going to draw in a second, for all the cases given a linear n by n system. And now our goal is to systematically create an augmented matrix and get 3 row operations, which are going to manipulate that augmented matrix, which represents our system. And then it's going to give us an equivalent system, which is going to give us the solution to both of them. And then we'll have a systematic method of solving n by n linear systems called Gaussian elimination. Okay, the goal of this section is to solve systematically linear systems. We can't quite get there. We have to squish this into this section and the next section, actually, because there's a whole lot of terminology. The goal is, first, let's point out that given a linear m by n system S, we're going to state this in the next section explicitly as a theorem. But for now, here's the nice flowchart for your mind. Given this system, either it has, this is Yoda says this is the law of excluded middles, do or do not, there is no try. Exactly. So a system either has solutions or it doesn't have solutions. If you have at least one solution, we call it consistent. If it doesn't have solutions, we call it inconsistent. So right there's the law of excluded middles. There's only 2 choices. The theorem that comes out of that is, that's an obvious one if you think about it. Either there's solutions or there isn't solutions. The beauty of the theorem that we're going to get will state that there was, in this scenario, if it's inconsistent, that's what we mean by no solutions. But if you're consistent, there can't be a bunch of different scenarios. There's only 2 scenarios for a system. It either has a unique solution or infinitely many solutions. And we're going to give a systematic way of finding which case we have and then giving explicitly the general solution to these systems. To do that, we're going to get this idea of turning a system into an augmented matrix, then doing 3 row operations to that augmented matrix to give us an equivalent form. And I just used the word, it's like, what are you talking about, equivalent form? It's like, exactly, we'll put that ahead of time and then you'll know what we mean. Once we get an equivalent form, it has the same solutions because we haven't changed any information along the way, cleverly. And then the solutions to this system are the same as the solutions to the original system, and then we have the solution to, the general solution to our arbitrary m by n linear system. That's going to be a whole lot of terminology, which we're going to break into 2 sections and multiple different definitions. Then we're going to have a systematic method called Gaussian Jordan elimination to take a linear system, put it into augmented matrix form, use 3 row operations to augment it into a reduced row echelon form or a row echelon form, and then deduce whether we have one solution, infinitely many solutions, or no solution. To start that story, the first definition we're going to get is 2 systems are called equivalent if they have the same general solutions. Then we want to ask ourselves, it's like, okay, you gave me a definition and no route to how to verify those types of things. What we're now going to give in equation form is the 3 things you're allowed to do to equations, which will give you an equivalent system. Let's do that. Okay, the goal is to state 3 equation operations, which we're immediately going to turn into and start calling row operations. So equation and row are synonyms immediately in our minds. We're going to go slow. We're going to state them as the equation operations. Then I'm going to tweak these slightly and explain how I've tweaked them to give us the 3 most efficient row operations once we have an augmented matrix. And then we're going to start manipulating rows in a matrix. I get to do some Neo stuff, and no, I don't think it has anything to do with that. What's the goal? Our goal is, after we do all of that, we're going to state these 3 equation operations or row operations. They're right here. What that will do for us is it'll allow us to manipulate our system, which you saw at the end of our previous recap video. We manipulate 3 systems just using one of these types of operations, and it allows us to have a simpler system, which is equivalent, we call it, which means they have the same solution, and therefore that allows us to find the general solution to that new simpler system, and of course, by default, because we've used only these row operations correctly, and in the order that I start having a mantra and telling you to use them in, we will get the solution to the original system as one. Those 3 equation operations in this form, which we're going to tweak slightly, but for now, the first 2 seem obvious. We've been saying this in all contexts from K to 12. What you do to one side of an equation, you do to the other side. In this case, what we're going to say is you can multiply both sides by a non-zero scalar. And we're just going to say you can multiply the whole equation by a non-zero scalar is how we say that. The next one is the best one. You can change the order in which you list the equations. By interchanging or flipping 2 equations or 2 rows, it's not going to change any of the information in the system. You've just relisted how you order them. Good. Yeah, that's one of the ones that you're allowed to use, and that's an easy one. So is the first one, multiply both sides by some non-zero scalar. If you multiply by 0, you get a tautology, 0 equals 0. That doesn't help us, and it kills information in the system. Our third one, which I used in the previous video 3 times in each equation, or each system, was to replace an equation by adding it to a multiple of another equation. Or in this case, technically the way we say that is that's already speeding up what we've done. Here, the thing that you're technically allowed to do is replace an equation with that equation added to another equation in the system. And because we're already allowed to use one, what we would first do is multiply the other equation by a non-zero scalar, then add it to that row or equation and replace that equation with that sum. You'll see in a second what. Yeah, there's a lot of terminology. Let's rephrase this entire thing now as an augmented matrix and row operations instead of equation operations. They're going to look the same but different. Given a linear n by n system S, this is what it's going to look like, and this is, hopefully you agree with what Gauss saw was there's too much and it's too busy. What he does is he eliminates all of the addition and subtraction. He eliminates the equal sign, he eliminates all the variables, and all he keeps is all the numbers. When we actually do this in a second, right now it's hard for you to see because it's all these A, I, J, and A11 guys, but these are all going to be a 2 and a 3 and a 0 and a numbers. So what we do is we take the system with all the variables and we create what we're going to call an augmented matrix. And the notation we're going to use is bracket A, column B. And then the column we're going to keep, because in general in the next chapter we're going to define what an arbitrary matrix is, and this is slightly different. We're not usually going to have a column here, so when we say augmented matrix we mean that there's an extra column here, and that's the equal sign, and that's why we put it there. It's representing, it's a different avatar for this linear system called the augmented matrix. And then as a good mathematician or a student, asking yourself, why did they pick the word matrix? What does matrix mean? And why did they pick matrix for the Neo movies? Matrix 4 has been postponed due to COVID to 2024 or something like that. But why are they picking the word matrix? It has nothing to do with actually the Matrix, the movies, and Neo, and that there would be some overall ambient structure which you couldn't tell that you were in, even though you are. Matrix literally means in Latin is when you take mat, which means mother, and rix, which means womb or pregnant, and you put those together, they created back then the word matrix, which meant the womb. So they've chose to use the word in Latin, which was the lingua franca then, the word matrix to describe this process. Why have they done this? What it does is it takes all the vital information from the system, and then it allows us to manipulate it, and it will give rise or give birth to the solution regardless of what kind of solution we have, regardless of whether it's one solution, no solution, or infinitely many. This process and this augmented matrix will always give us a systematic method of deciding which case we have, and if we have solutions, stating explicitly the general solution. This is why they chose the word matrix. Not because we want to know Kung Fu. I do want to know Kung Fu, but you got to do work, that's it. We also need the coefficient matrix. We aren't going to talk about it that much, but we also need the coefficient matrix, and then eventually what we're going to do at the end of chapter 2 is we're going to rephrase and have all of this matrix algebra that we're going to have, and we can define the coefficient matrix, the column vector B, and the unknown vector X, and what we're going to do is phrase this as a matrix equation. A matrix multiplication X equals B, and that's what our linear system becomes, as this shorthand equation where we have a coefficient matrix, this unknown solution vector that we're looking for, and this column vector B. And then what we're going to try and do systematically in chapter 2 is solve for X in this equation, matrix equation. But for now, with the equal sign in there, this is called the augmented matrix. Without the equal sign, if we get rid of that, essentially that is what we call the coefficient matrix, or this guy, it's all the coefficients standing in front of our unknown variables, so they call it the coefficient matrix. Now let's rephrase that we have an augmented matrix. Let's look at some examples, and then let's go through rephrasing the three equation operations as row operations. All right, before we rephrase the equation operations as row operations from an augmented matrix, let's look at some augmented matrices of some linear systems. So the plural of matrix is not matrices, it's matrices in English. I'm not sure what the Latin plural of matrix is. Conjugate the verb, I don't know English. Math is what we do. If I'm given, and again, hopefully you're recognizing I'm using the same 3 pedagogical linear 2x2 systems. This one has a unique solution, this one has infinitely many solutions, and this one has no solution. How do you know? You watch the previous video and you see this. Or we're going to get a systematic method using this now beast called augmented matrix. We're going to go through it in a few videos and get all the moving parts before we connect all the dots, and then by the end, in the last video of this in section 1.7, 2 videos from now, you'll see when you watch them that we have a systematic way of taking a system, augmenting a matrix, putting it into a magic form called Gaussian elimination to row echelon form, and then we can deduce whether we have one solution, no solution, infinitely many solutions. For this system, we just strip away all the variables, and ones and zeros seem to be the simpler ones, seem to give everyone the problems. This technically means what we never write it, 1 times x, and 1 times y, and 1 times x, and plus negative 1 times y equals 4 equals 3. So we just strip away all the variables x and y, the pluses and the equal signs, and we just keep the variables. Therefore, for this first system, the augmented matrix is 1, 1, 1, minus 1 would be the coefficient matrix. And then by adding the equals 4, 3, this is the augmented matrix of this linear 2x2 system. Same thing here. We take the 1, 1, 2, 2, that gives us the coefficient matrix, and then putting the equals in there gives us the augmented matrix of the system. Gesundheit. There's a cat sneezing in the background. Oh, now she's digging and purring, making a bed. In the last system, we see that we have 1, 1, 1, 1, and this is where you can start seeing eventually in this form that there's going to be a problem. When I subtract these equations, I can get 0 and 0 here, but then I'm going to get 3 minus 4 is negative 1, so I'm going to have 0 equals non-zero, and there's something bad here. So the augmented matrices, the idea is making an equivalent avatar, which makes everything much easier to look at and then manipulate. And then when we have these types of augmented matrices, we're going to rephrase the 3 row operations. You're allowed to manipulate these things to give us the general solution to the original systems. One more is, if there's a variable missing, technically what we mean is plus 0 times x2, so it is there. And the coefficient standing in front of the x2 is a 0, so we put that in there in the spot where x2 would be. This is what the augmented matrix of a linear system looks like. Now let's give the 3 row operations. Now we're going to phrase the three row operations of an augmented matrix. They're tweaked, essentially, these equation operations. The third one in particular, what we've done is we've taken the first equation and then done adding that. Once we do the multiplication by a non-zero scalar, then we can add that to another row. What are the three row operations now? You can multiply a row by a non-zero scalar, which means is we're going to place row j with k times row j for any row in the augmented matrix. What you can do is you can interchange two rows anytime you want. And then the third operation, which sounds weird at first, but which is what we've been doing already, is manipulating or adding and subtracting equations to get rid of things. You can replace a row with that row added to a multiple of another row. And what in symbolization, row I is going to go to row I plus k times row j. And this is the notation we'll use for interchanging two rows. Once we have this, what we're going to do is we're going to call the systematic method of augmenting a matrix and using these three row operations to put it into a specific form so that we can find the solution. This is called Gaussian elimination. And then if we get all the way to RREF, they add Jordan, which will be called Gaussian Jordan elimination. Let's look at now using these three operations and following Gauss's mantras to systematically give us a nice form, which we're now going to have to discuss, this row echelon form and reduced row echelon form, using these row operations to give this systematic solution to all linear m by n systems. Let's do that. All right, let's take the same three linear 2x2 systems and use this new machinery called the augmented matrix to try and find out how we're going to and what it's going to look like to give the general solution using this machinery. And we're still not done the notation. We still have 6 definitions left. So I'm hiding those. That'll be in the next video. But for now, let's start using this machinery and getting to what we're going to have this horrible terminology called the reduced row echelon form of an augmented matrix, so then we can read off what the solution is. For the first one, we have one solution. Infinitely many solutions, no solution. We already know this, which is good when you're trying to get a new technique. I already know what the answer is. I want the new machinery to give me the same thing, so then I'm pretty sure that this system was going to work systematically. It's going to. I said system a lot. 1. Immediately what do? I have the system, and you can see I put it in the different avatar, x1 and x2 instead of x and y. It doesn't matter to me. Hopefully it won't matter to you. So I have x1 plus x2 equals 4, and x1 minus x2 equals 3. I immediately augment the matrix. That gives me 1, 1, 4, 1 minus 1, 3, which we just saw. Now what do I do with that? Now what I'm going to do is, you start annotating. I want to Gauss's mantra. Now here's where we start getting ideas of good moves and bad moves. There is no such thing as good and bad, but it's not a race, but I'm winning. There's no good or bad moves, but you want to work as smart as you can, not hard. And we're going to get a systematic form, which we're going to call row echelon form, which we're going to train. I already know what that looks like. This is why I'm picking and following Gauss's mantras of the first move we always want to get is, up to a small caveat, get a leading 1 in the top left-hand corner. I have that for myself. We have it in all of them. I've done this for pedagogical reasons and to be nice on myself. Once I have that, kill below. Okay, don't use kill. Eliminate below. This is why it's called elimination. Remember, I just did it, and as soon as I start talking about this, you immediately forgot what the heck this represented. It's just another avatar for this. So this, if I want that to become a 0, that means I'm getting rid of this, is what's happening. And I want to get rid of that in the equation. So I want to start using row operations that I'm allowed to use to get that to be a 0. And the best way to make that a 0 is to have this one a 1 and multiply by the opposite to get rid of it. Long story short is, if I want to get rid of this 1, I now know I'm going to take row 2 and replace it with row 2 plus technically negative 1 times row 1, or what we say row 2 minus row 1, Leslie. And you're like, isn't it technically? Yes, because A minus B by definition is A plus the negative of B, which is A plus negative 1 times B. Axioms, properties. Therefore, yes, once I make that move, what does it give me? Now you have to start seeing what we're going to do is row operations. If you can't see it, write it down for yourself at first in each case. What I'm doing is I'm taking the entry of row 2 and subtracting it from row 1. So in the first spot, first of all, you can copy down row 1 because I'm not changing row 1, I'm changing row 2. Then I'm going to do 1 minus 1 is 0, the thing I wanted. That's why I did the move, because I wanted a 0 there. Now what happens? Well, I have to manipulate because we're adding this row to a multiple of another row. I do minus 1. Minus 1 is going to give me negative 2. And then I do 3 minus 4 gives me negative 1. I can essentially stop anytime I want, but I'm going to do one more move to make it nice and slick for myself. The next mantra is, once you have a 1 here and a 0 all the way below it, you move to the next non-zero column or row, and I want to make this a 1. I'm going to change this row by making this row be negative 1/2 times that row. What do I mean by that? We're going to take row 2 and replace it with negative 1/2 times row 2. What is that going to give me? Again, you will see to get to REF, you will never change row 1, which is good. One of them will always stay the same at first. And then what am I doing? I'm multiplying this one by negative 1/2. So 0 times negative 1/2 is still 0. Negative 2 times negative 1/2 is 1. That's why I did it. And then negative 1 times negative 1/2 is positive 1/2. Now that we have this, it's the forest for the trees scenario. You learn what an augmented matrix is, and then we give you these 3 row operations. You can manipulate this. We're going to get down to what we call a nice form, and we said it was row echelon form, and this is way too much. Regardless of the fact that it's going to have a nice name eventually, it's going to do the same thing for us. What this does is represents another simpler equivalent linear system to the original one. So if I go backwards again, and write this out as a system, I still have x1 plus x2 equals 4. I never manipulated that equation, so it's still the same information. This equation we did manipulate, and that says 0 times x1 plus 1 times x2 is equal to 1/2. Normally we don't write all that junk. We write, that is what I would write. And that tells me already the unique solution, part of the unique solution is that x2 was 1/2. And then, because I now know what this is, I get one equation and one unknown for x1, and I can solve, and I see that x1 is 7 over 2, and I get the unique solution to the system. The idea is to start putting the pieces together. Every time you get a system where we augment the matrix, we're going to use these 3 row operations. We're going to train in the next 2 videos systematically how to do this method correctly, called Gaussian elimination, to manipulate to row echelon form. Once I have that row echelon form, whatever it is, we're going to use the last row to decide whether we have a unique solution, infinitely many solutions, or no solution. Let's do the same thing, but with this one. All right, for the second one, now that you've sort of seen the game, I don't have to talk as much. I like to talk, but we can keep this at a minimum. Augment the matrix, it becomes Pavlovian. 1, 1, 4, 2, 2, 8. Now you can see the mantra is always get a leading 1 in the top left corner. I have that. Now I have to eliminate below. I want this 2 to become a 0. How am I going to do that? If I have a 1, now you can see the easiest way to do that is if I multiplied this row by negative 2, I would have 2 plus negative 2 is 0, and I would get a 0 there. And that's why I want a leading 1 always, so I can get rid of everyone below. These systems are going to get much bigger. At first we're doing 2 by 2, so you can see how the process goes. But these are going to get giant right away. What is that row operation? That says I'm going to replace row 2 with row 2 added to negative 2 times row 1. You also want to write that for when you hand in homework or on exams and stuff. That tells me if you make an error in here when you're adding and subtracting, this tells me what you were trying to do, even if you make a mistake along the way, because there will be mistakes. Hopefully I catch them all in my video. What does that give me? Again, as I said, to get to our first magic form, row echelon form, we never change row 1, or just the other rows. Now I'm going to manipulate this. 2 minus 2 is 0, and this one was nice and easy. 2 minus 2 is 0 again, so I'm distributing this onto everyone because we're multiplying the whole equation by negative 2, and then adding it to this row and replacing it. So I get 2 minus 2 again is 0, and then I get 8 minus 2 times 4, which is 8 minus 8, which is 0. This is now going to be, once we have our 3 mantras of what row echelon form is supposed to look like, next video, I can tell that this is row echelon form, so I stop and I say, what does this mean? This wasn't a 2 by 2 system, it was a 1 by 2 system. There's only one equation, and what does it tell me? It tells me x plus y equals 4, and more importantly here we focus on usually the second variable. What that says is 0 times y equals 0. Which is a tautology, which is always true regardless of what y is. So y is free to be anything, and it's a free variable. What that says is the general solution this time is going to be x is 4 minus t, y is t, the free variable. And what that means is there are infinitely many solutions. So in that last row of our magic form, if you have a row of zeros, there's one caveat which I'll have to point out when they're mean to you and give you an overdetermined system with more equations than unknowns. You might get a row of zeros but still have a unique solution. We'll deal with that one outlier scenario. Otherwise, when you get a row of zeros, it tells me I have infinitely many solutions, and the number of rows of zeros will be the number of free variables we have eventually. Now, what's the last case? What is this going to look like in its magic form at the end? And then our goal is going to be augment the matrix, get it into this form, and then use that last row of that form to tell whether I have one solution, infinitely many solutions, or no solution. Let's do the last one. All right, the last one already you can see we've done two. What's the first thing I should do? It hits a nerve in the back of my brain, and I augment the matrix 1, 1, 4, 1, 1, 3. Now my mantra immediately is get a 1 in the top left corner and get zeros below that. It's going to be the same as the first scenario because I have a 1 and a 1 and a 1 and a 1. Therefore, my move is going to be the same. I'm going to take row 2 and replace it with row 2 minus row 1, and this technically that's plus -1 times row 1. What does that give me now? Now you can see the problem. We're going to get 0 on this side and not 0 on that side, and that's an equation which everyone forgets, so that says bad, contradiction. 1, 1, 4. The first row didn't change. This one, 1 minus 1 is 0. 1 minus 1 is 0. 3 minus 4 is -1. If you really don't like the negative there, now multiply the row by -1, and I could get rid of it, but I'll leave it. What does that tell me? Everyone forgets, but that says x plus y equals 4 and 0 equals -1. Oh, I went back to x and y again. What it really says is 0 times x1 plus 0 times x2 equals -1. But this is 0 and this is 0, so this is 0 plus 0, which is 0. And then we can conclude that 0 equals -1. And that, may lightning strike you down, is a bad idea. We don't want 0 to equal 1. And what that technically says is this system has solutions if and only if 0 equals 1. We don't want that to be true, so this system has no solutions. But coincidentally, in the last row of this magic form that we're going to get in the next video is how I deduce the fact that this is what it should look like in one of the rows where we have a contradiction. You have zeros on the left-hand side of the equal sign and a non-zero number on the right-hand side, and that tells you you have no solutions and a contradiction and an inconsistent system. Please subscribe right here, hit the notification bell. In the next video, we're going to give Gaussian elimination and the reduced row echelon form to deduce whether we have one solution, no solution, infinitely many solutions. See you next time.